Hi everyone, welcome to Integral Calculus. Today we explore lesson 6.4, work done by a sprint. Number one, to study sprint, we need to know Hooke's law. The force required to keep the sprint in a compressed or stretched position x unit from the equilibrium position is proportional to x. That is fx equal k times x, where the positive constant k measures the stiffness of the spring. At equilibrium, x equal to 0. When we stretch the spring, x is more than 0 and the force is positive. When we compress the spring, x is less than 0 and the force is negative. The setup is this way because it helps us to set up the integral to compute the work, and the value of the integral will always be positive. The reason why we need integration is because force varies. The more we stretch a spring, the more force we use. Let's take a look at some example. Example 1. Suppose that a force of 10 Newton is required to stretch a spring 0.1 meter from its equilibrium position and hold in that position. Suppose that the spring obeys Hooke's law. Find the spring constant K. B. How much work is needed to compress the spring 0.5 meter from its equilibrium position? C. How much work is required to stretch the spring 0.25 meter from its equilibrium position? D. How much work is required to stretch the spring an extra 0.25 meter if it has already been stretched 0.1 meter from its equilibrium position? A. We know F equal to Kx, 10 equal to K times 0.1. Well, that is the force of 10 Newton required to stretch a spring 0.1 meter from its equilibrium position. From here, K is 100. So the force required to stretch the spring x distance is 100 times x. Now we can do B. We need to figure out the work needed to compress the spring. Work is integral. Force times distance. Force is 100 x, but it will be negative though because we are compressing. Right? Distance is dx. Compression force. And this would be the distance. Okay, integral will be compressing x is negative 0.5 to 0. Yay! Now we can find the antiderivative, which is negative 50 x squared. Evaluate from negative 0.5 to 0. Negative 50, 0 minus 0.5 square. And then from here, say negative times negative is positive. 12.5 joule. In C, we are stretching it. Stretching is gonna be integral. The force will be positive. So 100 x distance is dx, and then this would be stretching force distance. Stretching it from equilibrium to 0.25. 50x squared. Evaluate from 0 to 0.25. 50 times 0.25 square minus 0. And that gets us 3.125 joule. Pretty cool, huh? One more. So in D, we want to find a work to stretch it an extra 0.5 meter if it has already been stretched 1 meter. The work here would be integral of force times distance. Well, force is the same, right? Because we're stretching, it's going to be positive 100x. Distance dx. However, dx is going to be going from 0.1 to 0.1 plus 0.25. Yeah. So this integral from 0.1 to 0.35 100x dx, which is 50 x squared, 0.1 to 0.35, 50, 0.35 square minus 0.1 square, and that gives us 5.625 joule. Awesome. One more. Exercise 2. Suppose that 2 joule of work is needed to stretch a spring from its natural length of 30 centimeter to a length of 42 centimeter. How much work is needed to stretch the spring from 35 centimeter to 40 centimeter? B. How far beyond its natural length will a force of 30 Newton keep the spring stretched? Interesting. Let's take a look at A. So in order to do A, first thing is that we have to figure out the stiffness constant K. Step 1, find K. Well, we have to convert everything into meter. We know that we are stretching a spring from its natural length of 30 centimeter to a length of 42 centimeter. So the equilibrium level is at 30, and we can figure out the stretch distance. Equal 42 minus 30. 30 is equilibrium level. So this gives us the 12 centimeter, which is 0.12 meter. We know the work is 2 joule requiring for us to do that stretch. So work is integral from 0 to 0.12, because that is how far we stretch it beyond the equilibrium level. Fx dx, the work is 2 joule, and this would be integral 0 to 0.12. Force is kx dx. We can solve this one for k. 2 is k times x squared over 2. Evaluate this one from 0 to 0.12. 2 times k over 2, 0.12 square minus 0. And then from here, k would be I'm going to use an actual fraction here. 2500 over 9. Okay. So once we have K, then we can move on to step 2. And that is we're going to find the work needed to stretch the spring from 35 centimeter to 40 centimeter. Yeah, got to be careful here. We can only use the stretch distance from the equilibrium. So 35 centimeter is 5 centimeter from equilibrium. Because the equilibrium is at 30 centimeter, which gives us the lower limit to be 5 centimeter, 0.05 meter. And then 40 centimeter is 10 centimeter from equilibrium. This would give us the upper limit of the integral to be 10 centimeter, 0.1 meter. And so the work is integral from 0.05 to 0.1. Force time distance, well, we know K is 2500 over 9, so 2500 over 9. X, that is the force, the distance, dx. Stretch. Stretching force distance. Now we just have to evaluate this integral. Ta-da! Wow, amazing, huh? So 2500 over 9 times x squared over 2, evaluate from 0.05 to 0.1, which is 2500 over 18, 0.1 square minus 0.05 square, and this would give us 25 over 24 joule. Amazing. In exercise 2, part B, we are asked to answer the question, how far beyond its natural length will a force of 30 Newton keep the spring stretched? Well, this problem has nothing to do with work, so we don't have to use integration. It's just a simple substitution. It can be. We know force is kx, the force of 30 Newton. Then we know k, 2500 over 9, but we don't know x. That is it. Right? Simply solve for x there. So x could be 30 multiplied to the flip of 2500 over 9. So 9 over 2500, which is 0.108 meter. Now you can convert it to centimeter. And this would be 10.8 centimeter. Very cool. Thank you for watching. I hope you found the content useful. Please like and subscribe to help the channel grow. I will see you in the next video.